Okay, I got a really good question today, and I want to go over the answer with you guys. So this question has to do with finding the pH of a buffer, where you're working with a buffer in moles. So to give you guys an example, let's say I have 0.6 moles of my acid and 0.25 moles of my conjugate base, and I've put both of those into a 700 milliliter solution, and the Ka of my weak acid is this here. Okay, so to find the pH of this, I'm going to have to use an ice table. So the first ice table I'm going to show you, I'm going to make the ice table, and in it I'm going to put the values of the moles. Okay, so my 0.6 and my 0.25. So filling out my ice table, I have my plus x's, my minus x's. I go ahead and make the assumption, and then I put this into my K expression, and I solve for x, and my x is technically, so far what we've been thinking is the H plus concentration, okay, but it represents the H plus. So the question today in class was, well, Miss O, if everything that's in this table is moles, why isn't this moles, and why wouldn't we need to divide this by the volume of the solution to get to the actual concentration of H plus? Okay, and at the time I was kind of stumped, and I wanted to get to the bottom of this because I absolutely know that this number, without having to divide it, represents the H plus concentration, and I couldn't figure out why. So the first thing I did was ran a sample, just kind of like this, where I plugged in random numbers, and here's what would happen if you did it with molarity. Okay, so we're going to do the same problem. We have the moles over volume now. Okay, so now we've turned these into molarity, and I'm going to do the same ice table using molarity instead of moles. So here it is. I'm plugging into my K expression, and if you guys take a look now, absolutely we know for sure that if this is concentration, that my answer for X will be the concentration of H plus. And if you guys take a look, this is the 4.32 times 10 to the negative fifth number that I got up here. Okay, so what that tells us is we do not need to put this over the volume of the solution in order to get to the concentration. This answer is in fact the concentration of the H plus. Alright, so the question now becomes, well, how is it possible if we're doing this problem with moles and we get an answer in concentration? Okay, and the answer comes from what the definition of Ka is and how we can go about manipulating it. Okay, so for a moment I want you guys to take a look down here. We know that Ka is equal to the H plus times the A minus concentration over the undissociated acid. If I wanted to manipulate that to solve for the H plus, I would bring the HA up, and then I would divide the A minus out, and I would end up getting that guy right there. Okay? And it's actually, this is really important. Do you guys notice that it's the ratio between these two values that's important? So the Ka never changes, but it's the ratio between these two numbers that gets us the concentration of the H plus. So when we did this as the mole ratio up here, with the very first problem, our ratio was 0.25 and 0.6, so 0.25 and 0.6. What's that ratio? And then in the molarity version of it, we have 0.357 divided by 0.857. Okay, and if you crunch these out in your calculator, I actually haven't done that yet, but I'm pretty sure they are exactly the same number. They should be the same number. 0.357. Yep, so they both equal 0.416. So it doesn't matter if what you're putting into your K expression is in moles or in molarity, it's the ratio between the two that's important, and that's how we get the H plus concentration. Okay, so I hope that answers any questions or maybe threw some light on something you weren't thinking about.